So here we have a What the Physics video. This one is about vectors. So this is very exciting because we are using the smartboard. Woohoo! Yes, smartboard. Lovely. So to demonstrate the awesomeness of the smartboard, click. We have a game. Games make physics fun. I need a volunteer, please, to demonstrate how fun this is. Thank you, dear. Come on up, please. As you can see, we have some type of sorting activity here, where the left column is vector, and the right column is scalar. Well, scalar, really, but it's fun. It's even more fun to say scalar, right? And that's what we want. We want fun. So what you need to do, please, dear, is you need to see what's in your list at the bottom and drag them up into the correct category. And you can certainly do it by yourself if you want, or you can get assistance from others.
Okay.
Okay? So go to it.
Velocity's a vector.
Keep going, folks. Others. The acceleration is a vector, okay?
Force is a vector. So I think mass is a scalar.
Others can jump in too.
And I think displacement is also scalar.
Displacement's a vector.
No, wait, no, yeah. Displacement is vector.
Okay. Volume is a... What do we think of this? So, according to this, and we'll okay, I guess you can sit down for a moment. Velocity, acceleration, force, and displacement are in the vector category. In the scalar category, speed, time, volume, mass, distance, and temperature. Okay, so let's go ahead and check. Check. Yay! Ah, we're having fun. Okay, good. All right, so make sure that you filled in your list or drawn your arrows or something.
This is the best class ever, Fair. One person in the room got to stand up.
Okay, good, lovely. Let's move on. That was just a review of what we've already learned with vectors and scalars. Now, here's the graphical method of adding vectors. Guess what? I'm going to need another volunteer. Oh! No, really. You need a volunteer, please. Oh! It's going to hurt my voice if I keep doing that. If you'd like to choose someone, yes, since you went first.
Go.
Okay, that's the way it works. Sorry, but you get to choose next, okay?
I can help it, right?
Sure. It's fun. You guys are all afraid of things. What has happened to you if you've gotten something wrong before in this class?
I got it.
All right, so you got punched? Okay. For clarification purposes, no, that didn't happen. Okay. So starting from the x, and we can see what the big old X is, add the vectors. And which star are you going to end up at? So notice in red it says must add vectors tip to tail. So if I take this guy here you can see that over, how can I point? For recording purposes, let me go back over here. This guy right here is the tip, and this is the tail. Yes? Okay. I heard 2 people respond yes. Let's discuss that again. So this is the tip, and this is the so this is the and now it's the and this is the and now it's the and now it's the and here is the and this is the middle. Okay, good. Okay, so when we add tip to tail, what we need to do is move these around. So like here's the tip, and then we put in the tail, right? So from tip here to tail there, right? But I'm not gonna lead you astray. I'm not sure where you should start, which one you should start with. But you should choose one of these and start right there, and then we're gonna add up on we're gonna end up on a star. If you did it right, go ahead, sir. No pressure at all.
Go on top.
This one.
Yeah.
Okay.
Connect to the star.
So the tail is at the no. The tail. We're starting at the X. So the tail. You use that one. That's fine. The tail of that guy.
Use the one below it.
Yeah.
The tail of the vector needs to be at the center of the
Yeah,
X.
the one below it. The one in the middle. That's more. Yeah, that one.
This
All
one.
right.
Yeah.
Okay, so that one's tail is at the center of the X, right? Okay, so which one are you going to use next?
Now I'm going straight down. No. Up. No.
This one.
Yeah.
Right here.
No. You're adding these tip to tail. No.
I don't know.
Wait a second. They're not locked in position.
Okay, settle down, guys. Oh, get him.
Okay.
Okay,
This one goes on the tip on the other one.
so put that on the tip of the other one.
This one.
There we go. Lovely. Okay. Hey, stop the violence. Okay. So let's keep adding tip to tail. Yes.
Add another tip. To
All right.
tail. Tail to tip. Pick one. Eeny, meeny, miny, moe.
You are helpful, dear. Thank you so much. Okay. And then.
Pick the small. That's good.
Okay. Unfortunately, you have to use all of them.
No, don't do that.
Don't do that. You can if you want. It's just hard to see.
Take the small one out.
I don't like these activities.
Put that one going.
No, get that.
Down.
Get rid of that one too.
Which one?
The one that's on the next one. Get rid of it.
Yeah.
No. The one that's attached. The one attached.
on the line.
Yeah, get rid of that. Get the one pointing up, straight up. Yeah. Put that there.
Okay. And
The one
then.
that's slanted to the right. Yeah. Get the one that goes straight down.
Oh.
Get that.
Oh. Oh. Okay. Oh!
Pass it down now.
Yay! Applause! Okay. Now, you were all saying, "Oh no, you did it wrong, right? You did it wrong." Really? Well, let's see. Oops. Take that out. Well, this is giving me no love today. Put this one in its place. This is. I have to realign this thing. There, that works as well, right? So, what? Fair, you did that one wrong too, right? Okay. Well, let's see. I could have put this one here, and this one here, and that one there, and I could have done it actually any order, and it would have worked. So written down here in blue, it says, how can we add these vectors without knowing the order? Well, order don't matter. The order in which we add the vectors does not matter. Right. Okay. Oops. Yes. Okay, so that was adding vectors. When we add vectors, we add them tip to tail. When we subtract vectors, how are we going to do this? We cannot do tip to tip. We cannot do tail to tail. Vectors are designed to be added tip to tail. Okay? That's how they always have to be added. That's how we'd have to subtract them too, except for subtraction purposes, what are we going to do? Well, if we take a look at this and see 5 minus 3 equals 2, say, well, go. I can also look at this sentence and say 5 plus negative 3 equals 2, right? Is that a true statement? So what we're going to hopefully see is subtraction is really just the same thing as adding the negative or adding the opposite, right? So I'm still going to add vectors tip to tail, but what I'm going to see is in order to subtract them, I just need to flip around the vector, and then I will add it. Okay? Hopefully that just made sense. Okay? So if I wanted to say 5 minus 3, I'd have to add on 5 plus negative 3. Okay? All right, well, we'll try it out. So let's say we're flying. Okay? And if we're flying, we have a particular speed, and here's a lovely airplane picture. And we have the engine's velocity pushing us forward, yes? Okay. Well, who's ever been flying before? Okay, who has ever heard of the pilot saying like, oh, well, it should take this long to get there. And then later on the pilot says, oh, you know what, folks, there's some good conditions. We're able to get there a lot faster. Why do you think that is? Winds, right, okay. It's the winds are pushing us along. Or the winds might be throwing us off, right? They might be pushing us to the side, or who knows what. Okay, so let's take those guys into account. So, flying with a tailwind will increase your plane's overall velocity. So when we say a tailwind, we just imagine winds hitting our tail, right? It's pushing us along, yes? Okay, so we're just going to add the vectors together. What would it be if it were a headwind, do you think? Oh, headwind. Oh, that's the bird from Harry Potter, right? Headwind. It's been too long. You guys don't know who Harry Potter is? I'm sorry. Do I have to reference? Is Percy Jackson more recent? I don't know. It was Percy Jackson. Okay, forget it. I'm literally just not working now. Okay.
Decreases the velocity.
Yeah, I grew up when Judy Blume was the common author, but okay. So yeah, it would be slowing us down, kind of like the mood that is going on right now. So let's go ahead and get another volunteer. Hey, volunteers! If no one volunteers, then yes. Volunteer! Woohoo! Looks like you get to choose, sir.
Alright.
The benefit of, quote, volunteering.
Doesn't.
Oh, who doesn't? Yes. Make people into victims. That's nice. That's the benefit of smartboard. Okay.
Hey, John.
No names, please. No names.
No names. How about you?
Okay, thank you, volunteer. So it says use the long vector to show the plane's engine velocity and the short vector to show the wind's velocity. So what we're going to do is have, it says, an airplane flying with the tailwind. So this guy right here, this is the engine's velocity. So what you need to do is figure out which one would represent the tailwind and add it on tip to tail. So which way is the tailwind going to be going? Did you catch what we said earlier? Flying with the tailwind will increase the plane's... Oh, oh! Hey, what's going on there? No, don't unlock.
What? Okay.
What have you done? You've destroyed physics. Yay! Thank you very much.
So here.
Get it out.
It says lock. Oh wait, it says
I
lock.
wanted to lock it. I couldn't figure out how to lock it. Thank you. All right. Yes. All right. So it's locked. Good. Okay. All right. So put that back up here. Grab us this again. Here, we'll give you some more space there too. All right. So the tailwind. What did we say over here? Thank you for help, by the way, dear. The tailwind would increase the plane's velocity, right? So what do you think the direction should be? Let the record show people are pointing to the right.
No, wait.
That is the engine's velocity.
Wait, what?
They all go in. They
This
all
one?
go in that.
Yeah.
Oh.
No, but you added. So.
Oh, okay. All right, stop. No. All right, that is the guys. It did say the long one is the plane's velocity. Okay, so this one will be down here. So there's 3 different scenarios. Okay, you are using one of these. Yay! Okay, good. For an airplane flying with the headwind. Oh, yeah. Headwind is not a funny joke, apparently. Just click off to the side.
No, from tail to tip. Wait. Put the
Tip to tail, right?
tip to tail.
Tip to tail, not tip to tip.
No. Move it. No.
When we said no earlier, we meant it.
Just put the tail on the tip.
There we go.
Over just a tad. Hey, there we are. Okay, and then an airplane flying with wind blowing perpendicular to its... Yay, look at that. That was a smooth one. Well done, sir. Yay. So what are the resultants going to be? Well, the resultant guy here goes from the tail of the first to the tip of the last, yes? Okay. The resultant here goes from the tail of the first to the tip, there we are, out there, to the tip of the last. And the resultant here goes like, oh, that's a terrible straight line there. There we are. Okay. All right, so notice how are those are comparing? When we're adding the vectors, of course, the resultant is getting nice and big. Subtracting them is getting smaller and such. Okay? Hint for subtracting vectors. Okay? What we're supposed to be seeing here is the whole subtraction is really just adding the negative. So if I said actual numbers, let's say the engine velocity were 500 meters per second. Okay, that's really fast. That's preposterously fast. That's faster than the speed of sound. So let's say 100 meters per second. The wind velocity is 20 meters per second. Okay? If I say 100 plus 20, that's my first scenario that was drawn. That was this guy right up here. If I say, so that would be like saying 100 plus 20. This one would be like saying 100 minus 20, but because we cannot simply go tail to tail, what we're really saying is 100 plus negative 20. Okay? How did I do this one? Or how would I do this guy here? Well, they're not exactly on the same axis, are they? But what does this kind of look like now? Triangle, specifically a right triangle. So we'll be talking about the Pythagorean theorem. Right. Good, good, good. Okay, so adding several vectors. Oh, look, another volunteer. Use the provided vector arrows to add the vectors in the order and combinations listed. See how they compare. For clarification purposes, the short arrow is 2, the medium is 4, the long is 5. So, volunteer, please. Are you volunteering? Okay. Are you volunteering just so you can pick someone later?
No.
Okay.
Come on now.
Okay, so 1A.
Does it matter which way? Just do that.
Well, usually it'd say to the right is east. There we are. 2 meters east, and then 4 meters east. Okay. So drawing the resultant. Go ahead and we'll use red for the resultant. Just go from the tail of the first to the tip of the last. Okay. So what is that resultant going to be, by the way? 6
Meters.
East. Right. Okay. 6 meters east. So go ahead. Oh, I'm sorry. Hold on just a second, please. Go ahead and we'll write in 6 meters east. Okay. Well, that's a terrible E. Well, that's slightly better. Okay. Now go 5 meters west. Okay, from the tail of the first. Okay, good. So what is the resultant there going to be? 1 meter east. Excellent. Okay. 1B, 2 meters east, 4 meters east, and 5 meters west. Oh. Okay, why do you say everyone's like, oh, it's the same thing? Not exactly. I mean, the answer is the same thing, absolutely. But the commands were not exactly the same, right? What did I do for 1A? When I added the first two together, what did I have to do? I combined those first, and then I added on. What did you do? I look away for a moment, and you're like, whoa! but at least we're still recording. So there we are. Okay. I'm telling you, the 3 people that are going to watch this video are going to be really disappointed. Anyhow, in part A, we combined something and added it on, right? In part B, we just added them all individually. Okay, so what is our, oh, all right, sure, move it over, that's fine. Okay, well, she's ready for the result. So going from the tail of the first to the tip of the last. This is in 2 dimensions, though. Here, let's see. There we go. Okay. Starting here. There, that's what I was going for, right? Okay. So you say, oh, fair, I don't know what that length is going to be. Well, okay. We'll come back to it. How about B? Okay. You might say, oh, that's a little bit easier to see, right? And in case it's not super clear to people, okay. This was the 2 meters east part, right? So from here to here, what's that distance going to be? 3 meters, right? Okay. So 3 meters. What's this guy going to be here? 4 meters north, right? Okay, remember we had mentioned about triangles earlier. We could do Pythagorean theorem. We could also recognize it. Pythagorean triple. I don't know what that means. It's a special triangle, I think is what they call it. But go ahead and do the Pythagorean theorem, if you'd like. What's that? 5. Yeah, it's a 3, 4, 5 triangle, right? So this is 5 meters. You say, well, great, fair, but I don't know what the value of that upper one is. Well, what's this guy up here going to be? It's the same thing. So, it's 5 meters, but how are we supposed to know? Well, I can change up the order in which I add these things, and that won't matter. So, what did we learn here? Just like adding regular numbers, add vectors in different orders, and you can group them as well. So to summarize, order don't matter, and combinations don't matter. Thank you, volunteer, by the way. Okay. You keeping up all right? Hopefully. All right, so now we're going to do a little bit more numerically oriented. So hopefully the graphical method is a good explanation for us, and now we're moving on to some of the trig type stuff. Okay? Guess what I need?
Volunteer.
A volunteer! Oh! Yes. Volunteer? Hey, volunteer, thank you, dear. Come on up. Okay, so what you need to do, okay, so we see this is called the analytical method. You learn about these trig functions in geometry. Okay? When I say trig, you say, there, I'm not in trig yet. Ah, it's okay. We're just doing basic sine, cosine, tangent functions. Okay? When you get into trig and you take the secant squared of the something or another, that's not this. Okay? This is just SOHCAHTOA stuff, right? So, in math class, you learn that sine of theta is blank over blank. So what would we say in math class? All right, so in that, yeah, just grab one and drag it over. Yeah, it's infinite repeats. Opposite over hypotenuse. Excellent. Okay. Cosine is adjacent over hypotenuse. Lovely. And tan theta is right. All right. Okay, now in physics, I mean, it's not wrong to say opposite and hypotenuse and adjacent and such, but in physics, we're typically going to be using reference angle from the x-axis. So typically, we just need to say, hey, the opposite is going to be the y-axis, and the adjacent is going to be the x. And instead of saying hypotenuse, we're going to say r for resultant. Okay? So, go ahead and redo it in terms of physics, please. Okay? People are checking this. This is legitimate, right? Right. Okay. Good. Thank you very much. Yeah. Okay. So we're referencing stuff, new stuff from math, but it's all just review, right? Sure. Let's add some vectors that are perpendicular. Say, there, we've already done that. Well, we're going to do these not so much graphically, but a method called analytically. Analytically means we're using calculators. That's pretty much what it means. So if I walk 3 meters east and 2 meters north, what is my displacement going to be? You say, well, how would I do that? Well, first of all, I would draw out a sketch of a triangle to explain what I'm doing. So I'm saying I'm walking 3 meters east and 2 meters north, yeah? So there's my sketch. Hold this so we can kind of see, okay? So it's like I'm going there, and then my resultant is my hypotenuse, right? But it's helpful to visualize what's going on. The next thing I'm going to do is break these guys up into the x and y pieces. So I have 3 meters east. Well, I can't plug east into my calculator. If I say north, south, east, and west, yeah, that's effectively the same thing is saying 0, 90, 180, 270, and then 360 if you'd like. Okay, but the point is, if I'm saying east, pretty much just means 0 degrees. North, 90, so on. Okay? So, 3 meters at 0 degrees. That's on the x-axis, right? Would that be a positive direction or negative direction? Positive. So that would be a +3 on the x-axis. Any y aspect to it at all? No. So what I've got here is 3 for the x and 0 for the y. Then I'd say, okay, 2 meters at 90 degrees. Well, 90 degrees, that's on the y-axis. So that'd be like saying, what's my y component? Positive 2. What's my x component going to be? 0. So there I go. If I had more vectors, I could just keep adding those on as well. And we'll do examples of that, but later. My big values here, my big X and my big Y. Well, I'm going to add up all my little X's and get my big X. This one's easy to do. I'm hoping people realize that. What's 3 plus 0? What's 0 plus 2? 2. Awesome. There's my big X and my big Y. Okay? And I've got my sketch up here, and so hopefully it's making sense. This was the 3, this was the 2, and then I'm going to be looking for this result here, yeah? Okay? And yeah, they will get more complicated than this, just so you're aware. How would we combine these two guys together? With the Pythagorean theorem, right, okay. A squared plus B squared equals C squared, right? Yeah, I guess, but in physics, we're talking X, Y, and R, right? So X squared plus Y squared equals R squared. Same thing. Do the math, please. What do you get? Say again? Okay, oh, square root, okay, sorry. Square root of 30. In math, they love square roots and fractions and stuff like that. In physics, we like decimals. So, go. Yes. Okay. 3 point, I just put it as 2 digits. Really, I only gave you 1 digit in the first place, but that's kind of silly for a decimal in this case. 3.6 would be plenty, okay? Oh, and by the way, meters, right? Because I did give you meters in the first place. Now what about for the angle? People are like, oh, I got this one, fair. Northeast, right? Northeast implies exactly northeast, as in 45 degrees northeast. Is this 45 degrees northeast? No. So we can't just say just plain northeast. What we got to do, give a little more detail. How would we get that angle? We've got a triangle. Okay. I've got my y, I've got my x, and now I've got my r. That's fantastic. But now I want this angle theta. What trig function would deal with the x and the y, or the opposite and the adjacent? Tangent, right. So tan theta and we knew this from the previous slide, right? Tan theta is y over x. But I don't want tan theta. I want just plain theta. So you say, oh, that's fine. We'll divide through by tangent. Cannot divide through by tangent. Tangent is a function. That's like, how do you get rid of a square root? Oh, divide through by square root. No, there's no such thing. Okay? In order to get rid of a square root, you would square something, yeah? You do the reverse function. What's the reverse function of tangent? Arctangent is, or in your calculators, it's second tangent. Okay, that's fine. Okay, so in our calculators, we press second tan y divided by x. Okay, so this means our calculators need to be in a particular mode in order for this to work, right? Degrees! As far as we're concerned in this class, folks, we will not be using radians. Radians are stupid. Yeah, if you're in algebra 2, you don't even have to worry about switching back and forth. Okay, if you're in geometry, you don't have to worry about switching back and forth. If you're in trig, they'll probably want them in radians. What a pain. The degrees versus radians thing only matters when we're doing the trig stuff, though. It's not going to affect your adding, subtracting, square rooting stuff. Anywho, we get 33.7 degrees, I hope. If you did not, double check what mode you're in, and then double check your numbers and whatever you plugged in. Okay? Ooh. Ooh. Excellent. Now, how do we add vectors that are not perpendicular to each other? That's going to be a little bit more of a challenge. What we got to do is break things down into the x and y pieces. We're only going to do a little bit of this today. We're not going to finish this up. But this will help us on that handy guide to trig functions if you haven't done it already. So if I walk 3 meters east and then 2 meters at 60 degrees, what's my displacement? You say, oh, that's fine. Let's see, 3 squared plus 2 squared, and then take the square root, right? Can you do that? No, that's not a right triangle, so you cannot do that. Well, what I would do first is draw out what it looks like, just to see. Oh, that's not a right angle, right? So, and then 2, well, it's a little bit, not quite the right size, so I'll stretch that out a bit. Okay? And then my resultant is going to be up like this. Definitely not a right triangle. That doesn't mean I can't make it into a right triangle. You say, what? If I were to take this guy here and break it down into the x piece and the y piece, then all of a sudden, maybe I do have a right triangle. You say, physics. Yeah. How do I break it down into the x and y piece? I use trig, sine and cosine. Okay? Remember, and we've already discussed the sine and cosine, but as a reminder, what does sine of theta equal? Over y over r. Okay? Well, in this case, I'd be given the r and the theta. What if I want just the y? What would I do to solve for multiply both sides by r, right? So r equals, I'm sorry, I did that wrong. Excuse me. Y equals r times sine theta. I'm going to do the exact same thing with cosine. Finding space. Cosine of theta equals x over r. But I don't want cosine of theta. I want just plain x. It's going to be x equals r cosine theta. Okay, which is what I've written out down here. And it's also on the board in the room. Okay, if you take a look, it's on the top right. Okay. So, to help me remember all this, sometimes I will put the cosine above the x on my column here, and a sine above the y on my column there. And then what? Then I say 3 cosine 0, enter to my calculator. Tap, 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 please. What do I get? 3. You say, Fair, why did I even have to do that? I knew 3 meters at 0 degrees is just going to be 3 on the x-axis, right? Yeah, but I'm showing you this is always going to work. This way you don't have to remember a whole bunch of different rules. You just say like, oh, this is like my old reliable rule. If I want to get the y component, I'm going to say 3 sine 0. And what's that going to be? 0. Ta-da, right? Okay. Whether you needed it for that one or not, that might help, right? But this one, you're more likely to need it, right? 2 cos 60, enter. 1. Okay, and then 2 sine 60, enter. 1.732. Right. Okay. And it says that all up on here, just in case. Okay, so what we just did was break the vectors down into their little bitty pieces. The fancy way of saying pieces is components. You say, well, why would we do that? Well, now I've got all these little x's, and I've got all these little y's. If I add up all the little x's, what am I going to get? Well, yes, okay, I would get, sure. All right, well, let's go ahead and do that. Yes, I get 4, which is my big X. It's going to be on the x-axis, right? If I add up all my little y's, what am I going to get? Okay, column up 1.732, and that's on the y-axis. What do you think I'm going to be able to do with that? I'm going to be able to combine those using the Pythagorean theorem. Okay, which is, I just did that right there. So what do we do next? We draw a simple sketch of what it looks like. It doesn't have to be anything to scale, but it should be pretty reasonable. And then you don't have to get out a calculator and a protractor, but make it pretty good. And then I use the Pythagorean theorem. What do we get? I just put 4.4. But yes, I mean, there was only one significant digit to deal with in the first place, so I'm not being picky. But what about the angle? Quick, quick, quick. Second tangent, y over x.
23.4. Yeah.
Degrees. Excellent. Yes, yes. Awesome. Good stuff. Okay. Now to review. One last volunteer, please. You get to take our summarizing quiz. Volunteer! Yes, sir. All right, vectors are added. Tip to tail, tail to tail, tip to tip, or boys to men. Tip to all right, excellent. Say next.
Okay.
To break a vector down into x and y pieces, use the... Go ahead, guys, help them out. You have all the questions on your paper, folks. We're going to run out of time. Quick, quick, quick. Bell rings and we're not done. We're staying. We're done! There we are. Okay, next. Which one is not true?
The direction.
Everyone good?
Yay, next. All students take calculus. Now, you may not be familiar with this one. So, I mean, you specifically, but others might be. It's a creepy brainwashing technique to increase higher level math, or adding on the certain angles, or it's a mnemonic device, or all of these. Yeah.
Good guy. Oh, wow.
50%. Great job. An excellent effort. No, what's really funny is if you still miss, it's always supposed to be very positive. So even if you miss a whole bunch of them, it's like, hey, nice try.